Lesson 2. We are now going to look at permutations involving different objects. To begin, we will investigate arranging letters. Number 1. Two letters, A and B, can be written in two different orders, AB and BA. These are two permutations of A and B. Now list all of the permutations of three letters, A, B, and C. ABC, ACB, BAC, BCA, CAB, and CBA. From the last lesson, we can see there are three possibilities for the first letter. One is now gone, so we now have two possibilities for the second letter, and the one remaining possibility for the third letter. 3 times 2 times 1, which equals 6. Next, we want to list all the permutations of four letters. Try to see a logical Number 2. Instead of arranging letters in order, we can arrange objects if they are different. The word arrange in this question implies that order matters. How many different ways can 5 people be arranged in a line? We've seen this before. 5 times 4 times 3 times 2 times 1, which equals 120. Similarly, how many different ways can 5 different books be arranged on a shelf? 5 times 4 times 3 times 2 times 1, also 120. Again, how many different permutations are there in the letters of the word prove? Well, 5 times 4 times 3 times 2 times 1, again 120. For our next investigation, consider the letters A, B, C, D, and E. Instead of using all the letters to form the permutations, we can use fewer. For example, DB is a two-letter permutation of these 5 letters. We want to list all the different two-letter permutations of the 5 letters. AB, AC, AD, and so on. How many permutations are there? We can see by counting that there are 20. Let's see if we can calculate that. We have 5 possibilities for the first letter, leaving 4 possibilities for the second. Then we're done. 5 times 4 equals 20. Now predict how many 3-letter permutations there would be. We have 5 possibilities for the first letter, 4 possibilities for the second letter, leaving 3 possibilities for the third letter. We're done. 5 times 4 times 3 equals 60. Example 1. When you press the scramble button on a CD player, it plays a permutation of the songs on the CD. If the CD has 5 songs on it, how many permutations of the songs are possible? We will assume that we want to play all 5 songs. So we will have 5 possible songs for the first one, then a choice of 4 for the second, then 3, then 2, leaving the last one. 5 times 4 times 3 times 2 times 1 equals 120 different possibilities. We are done. Example 2. How many permutations can be formed using all of the letters of the word compute? We can count that there are 7 letters in the word, so we will start with 7 possibilities for the first letter, then a choice of 6 for the second, then 5, then 4, and so on. 7 times 6 times 5 times 4 times 3 times 2 times 1 gives us 5,040 possibilities. We are done. Factorial notation. As you can see, as the number of objects get large, the number of permutations also gets very large. Also, it can get very cumbersome to write out long strings of multiplications. Do we really want to arrange 50 objects and have to write out all the numbers right down to 1? Of course not. So, mathematicians have created a symbol. Let's start with the first 3. 1 factorial just equals 1. 2 factorial is 2 times 1, which of course is 2. 3 factorial is 3 times 2 times 1, which is equal to 6. Pause the video for a moment and see if you can write out 4 factorial and 5 factorial. In general, n factorial equals n times n minus 1 times n minus 2 times, and we keep on going until we end up at 1. So we're starting with the first number, and then we just keep multiplying by the next smaller number until we get down to 1. Pay attention to how this general equation looks. It will become important later. Now, let's revisit example 2, where we will arrange all 7 letters in the word compute. Instead of writing it all out as we did before, we just need to write a 7 with that explanation sign. 7 factorial, which is still 5,040. Most scientific calculators have a factorial function. Look for the symbol n factorial. Often, a second or shift key is required, and it is tricky to find on the graphing calculator. I have inserted an extra video in Blackboard to show this. (5b). Again, we are solving for x, and we have 6px equals 120. We fill in the formula as we did before. We would have 6 factorial on the top, 6 minus x factorial on the bottom, and it equals 120. In this case, the variable that we are trying to solve is in the bottom of the fraction. And we can think of the 120 as being 120 over 1, and we can actually cross multiply here. So if we do 6 factorial times 1, we just have 6 factorial equals, cross multiply the other two is 120 times 6 minus x factorial. And then we divide each side by 120, and we actually compute what 6 factorial is. We can throw that into our calculator to get 720, and we are left with 720 over 120 equals 6 minus x factorial. We do the division, and we get 6. So 6 now equals 6 minus x factorial. Now the real trick here is to get a factorial sign on both sides of the equal. And we do start recognizing these after a while, but you could always just start plugging in numbers in the calculator if you're unsure. But 6 is the same as 3 factorial. So I'm going to rewrite 6 as 3 factorial. We still have 6 minus x factorial on the other side. But because we have a factorial on each side of the equation, we can now cancel those out. So the 3 has to equal 6 minus x. And then doing the algebra, we would find that our answer would be x equals 3.